Hi everyone, I'm Gunnar Staples,
Sung Cho.
And I'm Jessie Sue.
and this is our Search for Solutions team project for Science and Global Change Scholars. Our project is about genetic engineering and how it can mediate some of the effects of climate change. There are a few benefits that genetic engineering has in respect to climate change. First, less greenhouse gases can be produced. Secondly, greenhouse gases can be sequestered from the atmosphere. And third, biofuels can be produced from biomass as well as greenhouse gases themselves.
Our Earth is governed by many cycles. Here we have the carbon cycle. Due to increasing fossil fuel burning, carbon dioxide is being stored in the atmosphere faster than the carbon cycle can naturally sequester it back out. This has caused phenomena such as global warming. Advances in genetic engineering allows us to artificially modify the carbon cycle, such as changing photosynthesis processes of plants for more efficient carbon dioxide removal.
One way to reduce greenhouse gases is to genetically engineer rice. Currently, agriculture is the second largest carbon footprint in the world, and nitrogen fertilizers account for a third of these emissions. However, modern science has found a way to genetically engineer rice to use less fertilizer. Some of the benefits are that less greenhouse gases are emitted into the atmosphere and farmers save money from using less fertilizer. The drawbacks are that genetically modified rice may yield a smaller crop than normal rice, and there may be potential or unseen health risks. Another method to reduce greenhouse gases is to genetically engineer flora. Human activities currently add 9 gigatons of carbon to the atmosphere per year. However, a new analysis published in the October issue of Bioscience suggests that 5 to 8 gigatons of carbon could be offset annually by genetically modified plants that optimize carbon sequestration. Carbon sequestration refers to the capture and long-term storage of atmospheric carbon dioxide. Plants take up carbon dioxide and store carbon in their biomass. In stems and leaves, carbon can stay for decades to centuries, whereas carbon stored in underground root systems can stay sequestered for millennia. Perennials and annuals are two potential candidates for better carbon sequestration. Perennials are more efficient than annuals at hiding carbon underground because they have a more extensive root system. However, since perenniality is a complex trait to modify, some scientists suggest that it may be easier to modify annuals instead. Here's a demonstration of the carbon sequestering cycle. First, atmospheric carbon is fixed in plants through photosynthesis. Some of the carbon is stored in the stems and leaves, while the rest is internally transferred to underground root systems. Eventually, the carbon is lost back into the atmosphere through respiration and decomposition. However, with genetically modified flora, carbon can be stored in plants' roots for a longer period of time.
Genetically modified plants can be utilized to change the photosynthesis pathway. Such benefits include increased carbon dioxide conversion of plants, decreased water and fertilizer needs of such plants. Carbon-eating forests are considered a plausible application of genetic engineering. These trees could decrease the carbon dioxide levels by half in 50 years.
Researchers at UCLA have modified cyanobacteria Xenococcus elongatus to use carbon dioxide and solar energy to turn the carbon dioxide into isobutanol. This is a fuel that could possibly be used to power cars in the future. There is a slight drawback in this process, however. That drawback is that isobutanol can already be made cheaply by a pre-existing method. This chart shows in detail how bacteria take carbon dioxide and turn it into isobutanol. Ethanol is another biofuel that shows promise as a gasoline alternative. Scientists have modified bacteria to create 50% more ethanol from sugar. This method also creates no carbon dioxide as a byproduct. However, this method needs to use hydrogen in order to work. In order to get this hydrogen, we currently get it from fossil fuels, and when we do this, it creates greenhouse gases, which doesn't make this method efficient. This chart details how bacteria turn biomass into ethanol. Now we have a video that shows how researchers are using bacteria to turn biomass into gasoline.
Led by Professor Lee Sang-yup, have demonstrated that E. coli can also be reprogrammed to produce a high-premium oil product. They're using the bacteria to make gasoline.
저희는 실제 자연계에서는 생산이 안 되지만 By using a strategic tool called metabolic engineering, we've conducted research on converting glucose, or waste biomass, directly into gasoline.
그러한 포도당이나 설탕을 이용해서
The glucose conversion produces chains of hydrocarbons similar to those found in conventional gasoline. At this stage, the process requires massive amounts of bacteria to produce just a few drops of fuel. But Lee says that with the concept proven, the team can now work on improving the process.
As you can see, genetic engineering holds promise to mediate the effects of, or even solving, climate change. However, there are still a lot of drawbacks, and more research is needed before there is a final solution. Thank you for watching our video.